Hi everyone, I'm Tumi Shiraji, presenting our paper titled A Systematic Error Assessment for Electricity Access Mapping with Nighttime Lights. Access to electricity is an important catalyst for development that has been shown to be correlated with a host of socioeconomic indicators. Currently, about 800 million people do not have access to electricity. Mapping electrification is useful for a number of reasons, including tracking the progress made in electrification, developing national plans, and identifying treated areas for impact assessments. However, this mapping has historically been challenging, and approaches have ranged from labor-intensive digitizing of network maps to costly and time-consuming surveys. Recently, nighttime light data has emerged as a cost-effective approach for mapping electrification, though it faces challenges such as the presence of noise. Moreover, we are unsure of how various characteristics of an area, such as the population density, influence the accuracy of these maps. In response to these challenges, our study presents a systematic error assessment of machine learning models used to develop electrification maps from nighttime lights. To develop this model, we use three sets of data. The first is nighttime light data from the VIRS instrument at a 450 spatial resolution collected at various temporal resolution. We identified electrified nighttime light pixels by referencing the location of electric meters and transformers sourced from utilities in Rwanda and Kenya. On the flip side, we identified pixels that are not electrified from zero radiance locations, such as water bodies and forests, identified using land use land cover products. This dataset formed the basis for training a random forest machine learning model for mapping electrification. Now let's dive into the main findings of our study. First, we investigated the optimal temporal resolution for mapping electrification with nighttime lights. We compared annual, quarterly, monthly, and daily images across a range of metrics and found that monthly resolution gave the best performance. Generally, increasing the temporal resolution improved the performance of the models up until we reach monthly aggregation. This is because daily images contain a lot of noise, resulting in an increased number of false positives. We investigated how the characteristics of electrified pixels impact their likelihood of being correctly classified. This chart compares the distribution of the number of meters in misclassified pixels with the distribution in the entire test dataset, revealing that pixels with fewer meters are more prone to misclassifications. The next chart shows the percentage of misclassified pixels as a function of time since electrification. The duration since electrification significantly influences the accuracy of pixel identification. Lastly, we calculated the average annual consumption in each pixel and found that while the accuracy of the model is around 80% for pixels with about 20 kilowatt hour annual consumption, the accuracy goes as high as 90% for pixels with an average consumption of about 200 kilowatt hours. Since we have data from two different countries in this study, we also assessed the generalization of a model trained on data from one country to other countries. We did this by first training and testing the model on data from one country to obtain baseline metrics. The data from the other country are then added in increments of 10%, after which the model is evaluated on the remaining data from the unseen country. We made two key observations here. First, the relatively flat profile of the scatter plots indicates that adding location-specific data has very little impact on the performance of the model. Therefore, the models should be able to generalize well to unseen countries. However, we also observed that we were able to achieve a balanced accuracy of about 94% in Kenya, while we only obtained 73% in Rwanda. We hypothesized that the reason for this is that the average consumption in Kenya is about 2 times that of Rwanda, so it is easier to separate pixels that are electrified from those that are not electrified in Kenya than it is in Rwanda. Lastly, we assessed the ability of our model to detect off-grid systems. For this, we used the location of about 350 operational mini-grids provided by ECOWAS Center for Renewable Energy and Energy Efficiency. We were able to detect about 92% of the mini-grids, indicating that the models trained with data from on-grid systems, transformers and meters, can be used to detect off-grid systems such as mini-grids.